Today, let me just begin by recalling a few facts from last time. So, what all have we done? We had started off with a set S, which is a sample space. So, this was the supposed to be all possible outcomes. And we defined this space of all events. So this is so an event E was essentially all subsets of S. So this, we had taken this temporary definition, all subsets of S. So, and also we had pointed out that it includes the empty set and the whole space. Because nothing happens, and S is just all possible outcomes. Anything happens. And then we defined P, which is the probability on S. Probability on S as a function P is a function from the event space to 0, 1. So it takes any event to 0, 1, and it had two axioms. One was that the probability of the whole sample space was equal to 1, and the second was that if you take EI, E1, E2, and so on and so forth, you take a countable sequence of disjoint events, then the probability of the union I equal to 1 to infinity of the EI is the sum from j equal to 1 to infinity of the probability of each. And this included several sort of nuances. That one was that the series on the right hand side here converges, and it's equal to the left hand side. And left hand side just says that if you have disjoint events, then the probabilities of disjoint events add up to give you probability into the excuse me. So now we will try to sort of build on this and do some basic properties of probability, which I'd like to sort of straighten before I do examples. So today I'll begin with some basic properties of probability. So here are some basic properties. So here's the first theorem that I'd like to show before I do examples. The first theorem that I'd like to show is sort of a longish theorem. Is the following: let P be a probability on a sample space S. Sorry for that, I made a mistake in the ink. Let P be a probability on a sample space S. Then the first property is that the probability of the empty set, that is nothing happens, is 0. The second thing is, like I said, probability is finitely additive. That is, if E1, E2 up to En are a finite collection of events, collection of disjoint events, then probability of union I equal to 1 to n EI is the sum from I equal to 1 to n probability. So this is a little different the definition of in the axiom, that here I require only for countable unions, but it's sort of a simple exercise which you will do to show that it also holds for any finite unions. Number 3 was that if E and F are events with E contained in F, then probability of E is less than equal to probability. So if an event is larger and contains a smaller event, its probability is larger also. The fourth is, if E and F are events and E is contained in F, then you can actually write the probability of F minus the probability of E is actually the set probability of F removed from E. So F minus the events. We keep that there. Number 5 is that if E complement, if E sub C is the complement of E, then probability of E complement is 1 minus the probability. And the last is, if E and F are events, then if you look at the union of F and E, that's going to be the probability of F plus probability of E minus the probability of E and F. Okay. So this is one theorem that I like to show. I'll show it in one shot, the whole theorem. You can see it in one shot. So this is one thing I'd like to show in this class. That is, sorry about that. So I'd like to show 1 through 6 and try and show you how the proof goes. And this, assuming just P is a probability sample space, that means it satisfies those two axioms that we start off with. Very nice. Okay, so let me now prove it. Okay. Here's the proof. Proof in black perhaps. So the first one is that the empty set probability is equal. So now this is something, it's a little trivial to understand. If I take E1 equal to the empty set, E2 equal to the empty set, and so on and so forth, this is a countable sequence of disjoint events, by definition. Is a countable sequence, 2 for 1, countable sequence of disjoint events. Okay. Once you have this, then you can apply axiom 2. So axiom 2 of definition implies probability of the countable union I equal to 1 to infinity EI is equal to the sum from j equal to 1 to infinity, the probability of EJ. Okay. I've used I and I actually just used same I, it's not a problem, so I use same I. Now if you notice, the right hand side, this particular portion right here, if I take union of empty sets, that's the same as the empty set again. And these are all empty sets. So in some sense, this just implies that the probability of the empty set is equal to the probability of empty set plus probability of the empty set, and so on and so forth. Okay. But we know that the right hand side converges. We know that by assumption, this right hand side should converge. Converges by axiom 2. We also know that by the axiom 1, by definition of probability, this is between 0 and 1. So now it's a simple exercise. If you have right hand side, you have some finite number, and right hand side you are having the same number many times. The only way this can be true is that this implies that the empty set has to be 0. Because empty set a little positive number, the right hand side would diverge, and we're adding the same thing again and again, and it's positive, so the left hand side has to be equal to 0. Left hand side is 0 means that probability if there's 0 means each of the quantities is 0 and you're done. The second thing is the following. What is the second thing? The second thing says that you should get, if you take finitely many guys, then the probability sums up. So let's do that. So here what I do is let E1 up E2 up to En be given. Then these are given to you. So then you define Ej to be the empty set for j bigger than equal to n. So you're given E1, E2, En, disjoint is given. Now if you take everybody empty set after j bigger than n plus 1, then this would clearly imply that E1, E2, En and En plus 1 and so on and so forth are a disjoint collection of sets. So now again, by axiom 2, I know that the probability of union I equal to 1 to infinity Ei is the same as the sum from I equal to 1 to infinity of probability Ei. But now you're in luck, because you have to make two observations. One observation is that observation A is the following. That union I equal to 1 to infinity Ei is the same as the first n, because after that everybody's empty. So this is union I equal to 1 to n of the Eis. And you also know the second observation is by part 1, probability of Ei is equal to 0 for all I bigger than equal to n plus 1. Right? Because after n plus 1, everybody is empty and the probability is 0. So these two would immediately imply, these two observations would imply that the probability of union I equal to 1 to n of the Ei. So the left hand side is just this, so that's clear. So let me erase it properly. Left hand side is just this, union I equal to 1 to n of the Ei is the same as the sum from I equal to 1 to n of the probability. Very nice. Because after some time everybody is empty, so this guy is 0. So in effect, this will only be the finite sum on the left hand side, and similarly here on the right hand side. Very nice, very good. Now let me show where was I? I was trying to show this theorem. So where I was number 3. Number 3 is if E and F are events with E contained in F, then probability E less than equal to probability of F. So we'll do that in a second. So I'll try and show 3 now. That if E is larger than F is larger than E, then probability E is less than probability. Now 3, 4 and 5 are kind of related, so we'll try and do it together, but I'll try and do separately also. So here's 3. So in 3 what I do is, I do the following. So E is contained in F. This implies F minus E, that is, you remove E from F, and E are disjoint by definition. And furthermore, you know, F minus E union E is the same as F. So therefore, if I take this to be my E1 and this to be my E2, you apply 2. So what do you get? You get probability of F minus E, on this side, F minus E union F on the left is the same as probability F minus E plus probability of F. But this implies what? On the left hand side, F minus E union F is just F, so I get F. On the right hand side, I get probability F minus E plus probability of E. Oh, sorry, it's E here. Sorry. E. So therefore, this whole thing would imply everything in one shot. This calculation. So let me erase this now. Let me just not call it 3. So let me just call it observe. So this calculation we'll observe this calculation that this happens. You apply 2, so you get star. Okay. Now we'll finish everything in one shot. So if you want to do 3 for 3, so what I'll do it in blue. I'm sorry. So if I do 3, so what do I do now? If I do from star as probability of f minus e is always non-negative, it's only between 0 and 1, this will imply immediately that probability of f is bigger than or equal to probability, which is what I want. That's immediate. And star readily implies 4. 4 is ready-made from star. So star readily implies. That's what 4 exactly said. How do you do 5? 5 again is from star again. In star, take how do you take? Take f equal to s. Take f equal to s. Then 5 is immediate, right? Because if you take f equal to s, you get probability of s is equal to probability of s minus e. That's probability of s minus e, which is e complement, plus probability of e. But probability of s is 1 from axiom 1. So I get probability of 1 is equal to this probability of e complement plus probability of e. So this would imply that probability of e is 1 minus the probability of e complement. Very nice. Very good. Now 6 is easy. 6 is easy. 6 is again you have to just work a little bit with star again and just do it properly. So what you do is you take E union F. So that's everybody in E and everybody in or in F. So that you can take it as everybody in E or everybody in F outside E. That's the same thing. There's no problem. So now you apply 2. What does 2 say? The 2 says probability of E union F is equal to probability of E plus probability of F minus E. So F minus E. And notice that they are disjoint sets. This disjoint unit, which I have used for 2. Because F minus E and E are disjoint by definition. So now once you have this, you're in shape now, right? Because you have this statement now. You also know that F minus E. Sorry, let me write down in black again. Sorry. You also know that F minus E is contained in F, right? And F minus E. F minus E is the same as those elements in F which are not in F minus E. That means they are in E also. That means this is just F and E. So therefore you're now in good shape now. Again, you have F minus E here. You have this guy here, right? So you can apply 4. What does 4 say? 4 says exactly this. Probability F minus E is exactly this. So you apply 4, right, with F and F minus A to get probability of F minus E, F minus of F minus E is equal to probability of F minus probability of F minus E. So to get, you apply with F and F minus E to get probability of F minus E is the same as probability of F minus the probability of F minus F minus E. But that's the same as probability of F minus, this is just F and E. So putting, let's call this as dagger and this as double dagger. So putting dagger and double dagger together, what do we get? We get probability of E union F is probability of E plus this person, but this person right here was equal to this person, so the same as plus probability of F minus probability of F. And that concludes the proof. So let's quickly recap. Let me make it double and so show it to you properly. So let me go back here. So here's the, let me go back to the previous page. So we start from here. So this is what we are. Let me make it a little smaller so you can see the whole thing in one page. Oops, sorry about that. Very nice. We come here, here. We'll make this a little smaller and go to page 3. Very nice. So left hand side clearly tells you that what you want to show. You want to show probability of empty set is 0. Nothing happens. That proof is quite straightforward. All you do is take E1, E2, all empty sets, a countable sequence. And once you do that, the axiom 2 implies the probability of countable union is sum of the probabilities. And that immediately implies that probability of empty set is equal to probability of empty set, to probability of empty set, and so on and so forth. But the right hand side converges absolutely, and we know that the probability in 0 and 1, the only way the equality can be true is probability of empty set is 0. That finishes off proof of 1. For the second part, you have to just use part 1. So what you do is you take E1, E2, En be the given sequence of disjoint sets. Then you define Ej to be empty for j bigger than or equal to n plus 1. Once you do that, you apply the axiom 2 of probability. Then you know that probability of the union I equal to 1 to infinity is sum of the probability of EIs. And once you do that, you're in business because the countable union is just the finite union because after some time everybody is empty after n plus 1 for surely. And you also know that the probability of empty set is 0. So this should be probability empty set is 0. I'm sorry, I made a mistake here. I should have said empty set is 0. Oops, sorry about that. So is equal to 0 for everybody around. That means the right hand side sum is only a finite sum till n. So probability union is equal to the finite sum. Then once you have this, to show 3, 4, and 5 is fairly straightforward. What you do is you make the following observation, that if E is contained in F, then F minus E and E are disjoint sets, and if you take E1 and E2 and apply 2, you get probability of F minus E union E, that is E1 union E2, is probability of E1 plus probability of E2. Once you do this, you take your probability of F on one side, is probability F minus E plus probability of F, probability. So using star, 3 is immediate because this guy is non-negative, so probability of F is bigger than probability of E. That's what star said, 3 said. So star gives you 3. 4 is exactly what star is because you just bring it on this side, probability F minus E is same as probability of E. In 5, you just take E to be the whole spaces. For 6, you have to be a little bit careful, but not that much. You first observe that E union F is E union F minus E. Once you do that, you apply 2 with these two sets, they're disjoint unions. So probability of E union F is probability of E plus probability of F minus E. But now what you do is, you know F minus E is contained in F, and F minus E is same as F and E. Using these two facts, you apply 4 with the sets F and F minus E. So if you look at 4, you get F and F minus E, you get F minus E is exactly this, which is F minus F minus E. That's exactly what I get. So I plug that in back in star and dagger and double dagger, and I get the answer. Very nice. So now let me do a quick example. I'll just sort of close this lecture. Do 2 examples. So one example is the following. let's go back to our original example. I'll just call this example 1.1.5. Here, a coin flip comes up heads or tails. Comes up heads or tails. That means S is either heads or tails. So let's try and see how to model it. Let's say a coin is fair if each of these outcomes is equally likely. Let's write that down. So let's say a coin is fair if every outcome in S is equally likely. So now we'll try and see if we can assign our probabilities to heads and tails. So now let's say E is heads and F is tails. So they're both single outcomes. So we know that if they're equally likely, this implies that, let's say, probability of E should be the same as probability of F, should be same as, let's call the value PS. But you also know from axiom 1 that 1 is equal to probability of S. That's axiom 1. But you also know that S is the same as E union F by definition. Let me write this in blue so that's kind of clear. It's axiom 1. 1 is equal to P union F. But if you use this, this theorem, what's it called? What do we call it? What's the theorem called? The theorem is, let's say, let me go back up, get the number down. Theorem 1.4.1.2. We come back down here. Theorem 1.1.42. What do you get? This is equal to probability of E. So let me write down is equal to probability of E plus probability of F. But each of these was P. This is equal to P plus P, and that's equal to 2P. So if you run through the calculation, you start off with 1, you end up at 2P. This would be true only if P was equal to half. So that means if you have a fair coin, the chance of getting heads is 50%. One simple operation. So let me begin with an example, just to recollect where we left off from last time. So this example 1.1.7. Suppose we know that there is a 60% chance that it will rain tomorrow. And 70% chance that the high temperature will be about 30 degrees Celsius. And suppose we also know that there's a 40% chance that it will rain tomorrow, and that the high temperature will be about 30 degrees. So I have these three facts. And the question I ask you is, how likely is it tomorrow will be a dry day, that is no rain, and how likely is it tomorrow will be a dry day, and the temperature, high temperature, does not go above about 30 degrees centigrade. Suppose I have to solve this question. So let me try and solve this question using the axioms of probability and what we did last time. So what you do is you set up properly. Just say let E be the event, it will rain tomorrow. Okay. F be the event that the high temperature is above 30 degrees centigrade. Okay. Let's take that are the two events, E and F. So if you look at the three things that I've said you, probability of E is 60%, that's 0.6. Probability of F is 70%, 0.7, and probability of E and F is 40%. So what we've given is probability of E is 0.6, probability of F is 0.7, and probability of E and F is 0.4. And what are we asking? How likely it will be a dry day tomorrow and the high temperature not go above 30. So what's the question asking you is, what's the chance that it will be a dry day, that is E complement, doesn't rain, and the chance that F, it doesn't go above, that F complement. This is what you're asking. So how does one do this problem? You look at this, so you get probability of E complement and F complement. That's the same as, so you observe that E complement and F complement is the same as E union F, the whole complement. That's the first observation, right? So as this happens, then you have this is equal to this F complement. But this you know from the previous exercise, I think it was 5 of, let me write down in black so it's clear. So it's 5 of theorem 1.1.4. Right? So this will be equal to 1 minus the chance of probability E union F. Now you can use 6 of the same theorem to get the same as 1 minus, inside is probability of E plus probability of F minus probability of E and F. So what's that going to be equal to now? That's going to be equal to 1 minus, this is 0.6, this is 0.7, right? And this is 0.4. So the whole thing is 0.9. So in fact, it is quite high that it will not rain. So it is 1 minus 0.9. So 1 minus 1 minus 0.9. So the answer is 0.9. So it's quite small that it will not be a dry, it will be a dry day, and it will not go above 30 degrees centigrade. Well,